So, the other day, we were taking a look at our total system. Because right now, we have a system of derangements we're claiming. Basically, the actions taken by the stuff that we use to create our realm of persistence. And right now, we're utilizing them as we have Planck TP equals 44 derangements. We have LP equals 35 derangements. We have charge, which is QP. It's equal to 18 derangements. We have the MP, mass Planck, equal to 8 derangements. And then we have the Planck temperature, big TP, because if you get these confused, you're going to be off by about 44 orders of magnitude, 76 orders of magnitude. I've done that a couple times. So it's usually a key right there. And that's 32 derangements. So the first time I came across this, I'm like, that's a bunch of derangements. And if that had the summation, notation, everything, I'm like, what does it add up to? Coincidentally, it does add up to 137 total derangements. And that number, for any of us that are the fans of physics, mathematics, and stuff like that, you're like, 137, oh yeah, because it has that association with the fine structure constant. Because when you do 1 over 137, it gives you a decently accurate out to so many decimal places of the fine structure constant. Now, that's not what we're actually going to be discussing that much. Okay, I lied. We're going to discuss it for about the next 60 seconds. So the reason why is we were taking a look at this the other day, and then Dad had pointed out, okay, we have, what if we start looking at this as squares? Because in Thad's lecture before, he was talking about squares. So you have 137 squared, and I just remember that it breaks down to basically, what was it, 105, and I think 88, something like that.
Sounds right.
88 or 81. So, yeah, so I think it was 88. If we're going to be looking at, in this case,
but they're both squared, right?
a triangle. I believe they are both squared. Okay, yeah, that should happen. Okay, so basically in this case, if we were to try to figure out how to square this, we have our a squared, so we'll do 105, we'll do 88. And as we were looking at these, we're looking for different relationships. How would these derangements, if we're going to say this is a fundamental part of what we're working on, how could we instantiate that? Because you can come up with whatever, depending on how much you want to put in, any number you want. It's just, how can you do it simply? So I started looking at these derangements, and I tried to figure out what might be going on. So what I did is I took all these things, and I did 44 over 137, and I kind of broke all these out. So it would add up to 1, and I'm like, I don't really see anything here. And I tried different combinations, mathematical things, multiply it by 2 pi or 4 pi, and just trying to see things. And I'd see some things, but nothing really that interesting. So then I started getting frustrated. So what I ended up doing, I'm just like, all right, what's some combination that I might be familiar with? And the combination I seem to be most familiar with is our box here with the x, our inversion boundary, because that is built in to pretty much all the constants we have over there. They'll have a right-hand side, and then that's expressed as 1 plus some action here with some combination of j's over here, and then we have it times 10 to the negative 7, or basically the magnitude of this inversion boundary. So what I did, after being very frustrated, just not being able to find anything there, I got desperate. So I took that inversion boundary that's made up of 1 Planck length, 1 Planck mass, and then 2 Planck charges in the denominator squared. So what I did naively, I took all the equations, I just threw them into my notebook and hoped for a miracle. I didn't get a miracle. Instead, I got an integer answer. Duh. Because when I put in the actual equations, I can toss them in the video, basically, they're all set equal to something. So it just took all the equal values and spit it out. And then after looking at that, I realized I didn't square the denominator. So I did that. So the form, when I ended up putting into Wolfram alpha was, all right, so I take the number of derangements of the Planck mass. That's 8. And then we multiply that by the number of derangements of the Planck length, 35. And then I put it over the Planck charge, 18 derangements, squared. And then I hit enter. And it gave me some crazy answer. It gave me something along the lines of, looked a little bit like Joe 1, but it was in the wrong decimal place. So it actually gave me, well, actually, to be fair, it gave me an integer fraction. So that equals 70 over 81. I looked at that. It meant absolutely nothing to me. So I looked further, and then the decimal answer it gives is some big, huge, crazy, repeating decimal. So it goes go 0, so make it messier, goes 0.8641975330, and that repeats in a period of 9. Some may consider forever. I personally don't believe forever because I believe we happen to exist in a finite realm. That's a personal opinion. But the point is, this form goes on and on, my friends. And if you notice here, this has all the numbers in it, except for 2. I have no idea what that means. That's the only thing that I know from observation. Okay, so that number again seems pretty cool. It's a repeating decimal. Those happen all the time. It has a somewhat interesting prime factorization. And that prime factorization is we have 2 times 3 raised to the negative 4 times 5 times 7. What does that mean? I don't know. My initial reaction is, well, okay, 5 and 7, that's the number of our dimensions. That's our break and scale symmetry. That also makes 35. Okay, that makes sense. Like 2, well, we're saying we have a double cover, some type of bounce here. 3, I don't know, my mind just goes to the vertices of our spatial dimensions, if you would. Negative 4, I don't know, is inversion of a hypersphere, 4th dimension.
Copying the 3518 squared by doing that. It's really just exactly the same thing.
Oh, that makes sense.
Yeah.
Cool. Another way to look at things. Okay. And again, what does that mean? It's, again, so you get the 70 over 81. We also get the next one that completely matches is 700 Wadsworth constants over 243. I don't know what that is. I see it all the time. It seems to pop up pretty much with integers and everything. Thad would know better than I would. I don't know what to make of that. But there was a third one that popped out that did catch my attention. And that was this. 35 over 6 times the 20 vertex entropy constant squared. I'm like, that was interesting, because this constant, the 20 vertex entropy constant, it always seemed to pop up in, like, when we were exploring different areas, it would pop up in decently interesting places, but it was never quite there. It just was never the best answer for anything we were looking for. Personally, I was like, why are you here? Why are you here? And then I found you here. Probably the last place I was expecting. And this is equal to that, which is equal to that, which is equal to that, because, well, at least for the first 60 some odd digits or so, it continues to repeat. I'm like, that's interesting. This was something that I was not expecting. And I'm like, okay, how the heck do I interpret something like this? Now, 35, I look at that, I'm like, well, we say that's the number of derangements for length or space. I'm like, all right, cool. I can have some concept of spaciness there. It's also 5 times break and scale symmetry, so other ways to go. I'm like, 6, well, that seems like a thing. And the 20 vertex entropy constant squared, so it seems to infer maybe there's 2 of these here. Okay, what the heck is a 20 vertex entropy constant? I'm glad somebody looked into it. Thanks Team Wolfram again. Okay, so where was that? Oh, here we go. 20. Nope, I close you. Okay, so the 20 vertex entropy constant is something that you'll pretty much only find on MathWorld or Wolfram Alpha, because it was basically coined, or at least named, the 20 vertex entropy constant within the MathWorld entry here. So basically it's describing an n by n triangular lattice with a wraparound. Oh, I mean, that's pretty cool right there. And then basically it has a number of orientations L, such that each vertex has 3 inwardly directed and 3 outwardly directed edges. I mean, such an orientation is said to consist of Eulerian orientation. And when you break it down, it ends up being like the square root. I'll put this on the thing. The square root of 27, yada yada. So 3 halves times the square root of 3. Okay. I mean, that was a whole bunch of math stuff. Where does it get interesting? Okay. It gets very interesting because when you actually go to the online encyclopedia of integer sequences, this is a very interesting thing because equivalently, the area in the complex plane of the smallest convex set containing all 6 roots of unity. I'm like, weren't we just talking about something that had 6 roots of unity? I mean, isn't that just our friend here, the imaginary golden ratio? I made that terrible, but yeah, okay. But
through the middle.
yeah. There we go. Okay. Imaginary golden ratio. There's your little tail. Cool. Okay. And that has the 6 roots. Basically, if you start over here, it's 1, 2, 3, 4, 5, and 6. Oh, okay. It's got 6 roots on me. Oh, that kind of sounds like a hexagon or something like that. Apparently, it's very easy to build things if they happen to have 6 sides or something. Okay. Now, I see that and I'm like, so I got 20 vertexes. Oh, no, actually, no, we're skipping ahead here. I'm sorry, I'm getting excited. Okay, also here, subtracting 2.5, i.e. the first 2 digits, we attain 0.9807, which is a limiting mean cluster density for the bond percolation model at probability 1/2. So what I'm hearing is it sounds like there seems to be a limit for a lattice at 1/2 probability. I'm like, Well, what if we doubled that? We would get a probability of 1. Is that a double cover of something to lead to a 1? I don't know. But one of the other interesting things is these next two things just kind of blew my mind. This constant is also the minimum radius of curvature of the exponential curve occurring at x equals negative log 2 divided by 2. It's like, oh, that's very interesting. Log of 2 divided by 2. Okay. And then we get really, really interesting. Apparently, Lumet proves that this is the critical impact parameter of a bare black hole. In multiples of the Schwarzschild radius, that is, light from a distant source coming towards a black hole is captured by the black hole at smaller distances and deflected at larger distances. And that was updated last year. So this is, I've seen this thing pop up for like over the past year and a half, and I'm like, I don't know. And they're still finding out stuff about it, apparently. The last interesting thing is, for any ABC triangle, sine A plus sine B plus sine C, basically, it's 3 times the square root of basically, it's symbolism there. Equality is obtained only when the triangle is equilateral. Okay, so it sounds like there's some balance there. Okay, we're done just blatantly reading off of that. So I'm like, how do I interpret this? I'm like, all right, you get space divided by something 20 with vertices, maybe 2 of them, and then 6. I'm like, well, if you get 20 vertices, you multiply that by 6, you get 120. So I type into the Googles 120 vertex polyhedron. Lo and behold, what pops up? A friend that other folks have mentioned before. As far as I understand, they're now to be nameless at the moment collaborator of the physics monastery had pointed some of these things out. But I found something very interesting. It's called the room here. It's called the 120 cell, because it is made up of 120 dodecahedrons at the vertices. I'm like, wait a second, dodecahedron? Isn't that a platonic solid? Yes, it is, Echelon. Coincidentally, this 120 cell seems to have at least one of all the platonic solids going up through the 4th dimension. That's very interesting. Now again, do I necessarily know what this means? Maybe this is just a completely random coincidence, because I don't know about you all, because I never had the urge at getting up before being like, you know what? I want to see what 70 divided by 81 is. I didn't care. I didn't care at all. It meant nothing to me. And then randomly I go into Wolfram Alpha and I'm like, oh, I'm so used to seeing things. I'm like, oh, 7 significant digits. Exciting. Maybe 14 significant digits. And I'm like, this is completely equal to that. What? And again, maybe just absolutely nothing there. But when you start going through it, not only do you have all those polyhedra, they describe it as the Swiss Army knife, quote unquote, because it has one of everything in it.
And I always love to mention 120 happens to be
5 factorial.
Yeah, and there's 5 little things that fit together. So all of the ways those factorize could fit that structure.
We take the derangements of 5, we get our 44. If we put our exclamation point and do factorial on the other side, it's 120. I mean, that's very neat. And it gets neater because it is made of the first sequence is the 5 cell, which is basically, it's a 4-dimensional tetrahedron. I'm like, wait a second. Is the hyperbolic figure 8 not made of like 2 tetrahedron? I'm like, That's very neat. Okay, but I mean, it's there. They basically just continue to build into each other, and we're still exploring this right now. But there's a lot of information, and coincidentally, Thad was talking in the lecture before this about the golden ratio, the imaginary golden ratio, I, and when you actually start to break down its vertices, the coordinates, and the permutations, I don't know about you, but that's phi. That's the golden ratio. Oh, that's the golden ratio, -2. Oh, the square root of 5, all over there. It pops up all over the place, and once we get a better idea about what might be going on, but also has literal mapped coordinates. So if you were to think of this as like the Earth or something like that, assuming it was kind of maybe more spherical than what it is right now, you have a North Pole that corresponds to one cell, okay? And you go through the meridians, you have an equator, and then you get to the South Pole, which is also one cell. It's interesting. They also have the winding rings, and this was the thing that I'm like, wait a second. I think I've seen this guy before. I think I saw this on the board last week. Now again, maybe just absolutely, I don't know. It's just when I start seeing, oh, okay, this seems like kind of like our hypercone right here. It just happens to be expressed in this particular geometry. Okay, well, I see a torus over there. All right, well, there seems to be 10 of those guys. We're assuming some form of a double cover. Okay, that's interesting. And then you just see, the animations are beautiful, and again, I've seen some of these things before, and when you see something like that, you're like, oh, that's so beautiful. I totally want that to be the answer. I mean, that would be fantastic, but it's like, my dad, God rest his soul, he was an attorney. He said, you follow the evidence. The evidence that I followed was because I made an assumption our derangements have an important action here. And I did one of our most important actions. And for any of the other ones, I haven't found anything yet. I don't know. But if we claim that that action is going to be important, we would expect maybe something interesting would happen. And when I don't know, I think this is the only time this really ever happened, but it's like, all right, I have 70 over 81. All right, that's cool. This other thing I can't parse. I'm like, that is oddly specific, and I've never seen it do that before. That's interesting. Now, I'm not saying we literally needed to go into the Platonic realm of concepts to get the concept of a higher dimensional Platonic solid, but I think it was John Bays we were listening to last week. He was kind of describing this because he said, once you hit 120, dodecahedrons, all of a sudden you look at this, it's this crazy thing. It just kind of looks like a starfish going out in multiple directions. He's like, yes, now immerse it in 4 dimensions. I'm like, I don't know how to do that. But then he goes around and starts showing the actual, I think this was the exact picture he used. He's like, it's something like that. This exact picture off of Wikipedia because, well, you can use it for free because it's Wikipedia. But you look into this and you realize, well, if this is hyperbolic, depending on where you are, would adjust your frame of reference. And that's when we have the picture on the inside. So I'll play this along for the video and everything. But you just look at that, it's like, you're assumed you're somewhere in the center and there's a rotation. And it's like, Well, I do hear folks like Professor Segman and other folks saying that, well, we only perceive the world because of how we adapted, because if we were able to see the world like it actually is, like, our heads would explode. Personally, I think we should have less heads exploding. At least in actuality. But this is a very interesting thing. Again, the only reason I kind of went down that path is you see certain things and you're like, oh, I want this to be true, and then you can justify whatever reasons you want. I just happen to just throw in what we're claiming happened to be important. 8 derangements for the Planck mass boundary, 35 derangements for the time, times 18 derangements for the charge boundary squared. And this happened to pop out. So, am I saying there's anything actually there? I'm inferring things. I could see a potential path. It's a very interesting coincidence. I think we'll just leave it at that right now. So, any questions, comments?
Oh, we had the 10588.
Mm-hmm.
There was more to say on that, right? 88 is 2 times 44, and 105 is 3 times 35.
Oh yeah. It also comes out for some of the I think equations for that too. Like 105 is in there too. That's I mean that's really all I kind of went off on. I started going down this path and I didn't really explore it that much more. Well, especially after I found that. Is there anything you want to add?
Probably because it's hard to see in 2 dimensions.
It's yes. Because I mean, anybody who's watching this video, I mean, you're watching on a screen. I mean, most things seem pretty flat to us. We can gauge some additional dimensionality, and it's like, all right, so even if you have 2 dimensions, you can add an extra dimension there. What the heck does 4 mean? I don't know. To me, that kind of means, what if I'm viewing this from the outside? Kind of like the whole like Flatlander thing, where it's like, if you're embedded within the system, it's kind of hard to try to imagine the system, especially if you're not used to it. So that's where all the cool animations come out, and it's hard to argue with code. So that's all we got.
Cool.
Thank you. All right. Let's see.